I'm going to use a 4053 analog multiplex or demultiplex IC, which has 3 single-pole double-throw analog switches built in, and I'm going to use this in an experiment to try switching the sequence of 2 guitar effect pedals and just using the oscilloscope to observe the difference in the signals as things are switched. So with guitar effects, you can take a guitar signal, plug it into an effect like this spring reverb, take the output, plug that into another effect, and then finally take the output of that, bring it to an amplifier. Then if you want either or both of the effects on or off, you just press those switches to control them. But if you also want the ability to swap the sequence, so the guitar signal now goes into a different effect, then to the other, and then out, depending which way you do this, you might get a different sound. So that's why I want to try to use the 4053 to swap the order of effects. And in this experiment, I have the 4053 on a PCB and this audio octave generator circuit with the transformer. So that's going to control the switching as well as become one of the 2 audio effects. There's a header here to send audio out so I can plug it into an effect and bring audio back in. And I'm doing this experiment with today's sponsor, PCBWay. The schematic for this circuit board evolved from a previous design where I had a transistor buffer which takes an audio signal, sends it to a transformer where it gets rectified, and depending on the traits of the signal, sometimes the output audio has audio that's an octave higher at twice the frequency. It all depends on the signal level, and it works better as this is more of a pure sine wave, and it's easier to get a double frequency sine wave when you rectify. So depending what you're doing, every so often you might get this octave up effect on your guitar signal. So then we just have another amplifier here with an op amp, and that helps overcome any losses in the transformer as well as losses from these diode drops to make sure we don't lose overall signal level. And I want to be able to zoom in a little, so I'll get this bottom section out of the way. We just have a VREF op amp buffer here, unity gain, and 2 resistors of equal value between 9 volts and ground. So we get around 4.5 volts, and then we buffer it with an op amp to get an ideal low impedance reference voltage that we can use to bias our audio signal halfway from 9 volts to ground. Then when we have a DC block capacitor, we can rebias the audio signal halfway between voltage rails and not clip the signal going through any of our amplifiers. Here's the 4053 switching circuit. So this octave generator up here is considered one guitar effect circuit, and in this experiment I'm going to take this off-board distortion effect as a second one, and the 4053 can swap the ordering in the signal chain between the distortion or the octave. I have a block diagram I can look at to help make this switching circuit make more sense, but we have headers here so we can have 9 volt power. This is the control switch which controls if the signal is being routed to one path or the other on all 3 audio switches here. So that's going to go to a toggle switch where the signal is either pulled up to 9 volts or grounded to change the signal path. Then we have a main audio in and out header, as well as an auxiliary audio in and out path. So basically, a guitar signal can come in on the main in, go through this whole switching network, get sent out to that external effect, come back in. These 2 effects are going to be swapped by position based on the control switch, and then main audio out can go to a guitar amplifier. One thing to note is any audio signals leaving this board or entering this board should have a DC block capacitor to make sure no DC voltage enters or leaves this board and messes up voltage biasing. So at the same time, when we have blocked DC, we need to make sure we rebias all of these audio paths. So I'm taking a 510K resistor, connecting it to VREF, which is that op amp down there with a low impedance 4.5 volt supply. All of these 510K resistors will allow the audio signals to rebias up halfway between 0 and 9, and the 510K keeps them from interfering with each other. This is a block diagram representation of the whole point of this project. So we have a guitar signal coming in, and we have two guitar effect circuits and then an output to go to an amplifier. So using our 4053 switch, we're able to interchange whether the guitar signal goes into effect 1 and then 2 and then out, or it goes to effect 2, then 1 and then out, because it can sound different and give different results. So having configuration like this with a switch can be a good feature. So in this 4053 routing path, this is our original audio signal coming in. This is the final audio signal going out to an amplifier, and whatever we're calling effect 1 or effect 2, one of these is the onboard transformer octave generating circuit, and the other one is the connector jack going to an external effect, like a fuzz or distortion, most likely in this case. The 4053 has 3 single pole double throw switches that all move together with a single control pin, whether it's high or low. It'll change whether all 3 of these switch contacts are going to the one terminal or to the other. So let's say the control is set so that all of these switches are connecting to the upper terminal. In that case, what we get is audio signal coming in. It's going to the top terminal, which means it's wired to go into the input of effect circuit number 1. It also connects over here to this bottom switch terminal, but if the switches are up, this really goes nowhere. So the signal comes in, goes into effect 1, then the output goes to another switch, and we are connected to the top. So that comes here. It's wired to the bottom terminal here, but again, it's going nowhere right now. So this output effect number 1 actually goes now to the input of effect 2. The output of that is routed to the main final output. Again, it also wires to this terminal, but right now it's not connected. So all the contacts are up, guitar signal goes into effect 1, then effect 2, and then out to an amplifier. If we change the control, so all of these switches are now connecting only to the bottom terminal, the guitar signal comes in, now it's routed down to the input of effect 2, the output is now routed to the input of effect 1, and the output of that is now routed down to the main out. So we've exchanged effect 1 and effect 2 like these two options here. So when I get the final circuit made and put into a stomp box, I think I'm just going to have a toggle switch on the box. I don't need to be able to change this order on the fly for my purposes. At least I don't think so. So I'm going to start out probably with a toggle switch to swap the configuration, and then using actual stomp switches on the effect box, I can do things like turn the overall effect on and off. Here is the test setup, which looks like a mess, and it's hard to show this, so I'm showing a long distance view toward the scope for now as an overview. I'm using a sine wave signal coming into the circuit board that does the audio switching and has the octave generator. The aux outputs go to this distortion effect here. So when I turn on this external distortion, we can see, for example, on the scope what'll happen. Now it's on, so we have this distorted green trace. Turn it back off. We just have this cleaner sine wave looking signal. And I have a DuPont wire here, which is the control pin for the 4053 switches. So when the wire is floating, the onboard pull-up keeps the control signal high, but I can ground it on this breadboard here, and it will change the signal path. So here is the blue incoming sine wave at 1 kilohertz. The green trace is the final output of the circuit after everything has been done to the signal. So right now the external effect circuit is bypassed, so it's a straight wire, and all we're doing is using the onboard octave generator effect. And if I control the final output level pot, I can go all the way down to nothing or around unity gain, or in this case, I can get above unity gain. Now I'm going to turn on the red trace. It's showing basically a duplicate of the blue sine wave. I offset it slightly just so we can clearly see the two different traces. This red trace is showing the signal exiting the octave generator board, going to the input of the external second effect. So in this case, the red signal is going into the distortion effect. Because we're seeing the red trace looking exactly like the input sine wave, that means the 4053 switches are configured to take the main input blue audio trace, send that directly out to the external distortion effect. So we're seeing the red trace being that same signal. And since that effect is turned off, it's just bypassed. So we get, again, the same sine wave coming back into the circuit, and then that goes to the octave generator as effect number 2, and we get this octave sine wave. So now if I turn on the external distortion, we're still sending out the incoming sine wave into the distortion, and that distortion is coming back in and then going to the octave circuit. So we're seeing this distorted sine wave, and it's at twice the frequency of the blue incoming sine wave. So if I turn that back off, now I'm going to change the 4053 switch control. I just grounded the control pin instead of having it pulled up. Now what we're seeing, again, the external distortion is bypassed. So it's a straight wire. So now we still have our blue incoming sine wave and the red trace being sent out to the distortion. It now looks like this green double frequency octave signal, because what we're doing now is routing this input sine wave first into the onboard octave generator, and then we send that, which is the red trace, out to the distortion. And being bypassed, it comes back in the same way, and that is our final effect in the chain. Now if I turn on distortion, the only thing that changed is the green final output of the circuit. So again, blue original sine wave, it's first going to the onboard octave generator. So again, the red trace, we're sending out twice the frequency of the original sine wave, still clean. It goes into the distortion, gets distorted, comes back into the PCB. Then our final green output trace, we're clearly seeing twice the frequency of the original blue sine wave. And we got all these little peaks here on the positive and negative parts of that signal. So again, if I change the configuration of the 4053 by setting the control high, again, we can tell by looking at the red trace, we currently have this set up so the main audio blue signal is sent first cleanly into the distortion off board, comes back in, goes to the octave generator, and the green trace is the result. Flip the switch on the 4053, we change the order. Now we're going first to the octave, sending that out to distortion, comes back in distorted, and looks different than the other configuration. So that's where we can see there's a different signal depending if we put octave into distortion or distortion into octave. And that's the purpose of this whole experiment with the 4053 signal routing. The green trace here is a lower amplitude than the other order, where it's clearly way louder than the original versus quieter than the original. But there's controls on that distortion effect. Right now I'm changing the tone control, letting more signal through, so we can obviously get, again, way louder than the original. And there's more work to be done, but so far the project seems to be evolving with good results.